In this video, we're going to take a look at some of the simple diode models that can be used as equivalent circuits when analyzing any kind of electronic circuit with a diode or several diodes in it. So we start by looking at the ideal diode model. So you can see here on the screen we have the circuit symbol for a diode. So that's just very simple triangle which points in the direction of current and a line. And we can see we've got here labeled the anode and the cathode, so this is the positive terminal on the left, negative terminal on the right. And the diode polarity, as you'll find out, is going to become very important because the way it's biased is essential to how it operates. The simplest model of a diode is to assume that it's completely ideal. So it behaves as a kind of perfect valve that will only allow current to flow through in one direction and completely blocks it in the other direction. So that's what we have here, the IV characteristic of the ideal diode model in the middle of the screen. So you can see it's quite straightforward, essentially made up of just two lines that cover the reverse bias and the forward bias conditions. So what do we mean by that? Well, in the reverse bias, we're considering the case where the voltage on the right hand side here would be larger than the voltage on the left hand side. So our V, as signified on the circuit symbol here, will be less than 0. So if V is negative. And in that condition, the ideal diode will act as an open circuit. So the equivalent circuit is simply an open circuit as shown here. In that case, of course, we can say that I is going to equal 0. Okay, you're going to get no current flowing through an open circuit, has effectively infinite resistance, as we have no connection between those two nodes. And we can see that in the graph, as our V goes less than 0, that's the left side of the graph, that's our reverse bias condition, and our I is maintained at 0 throughout. So what we're saying there is that no current can flow when in reverse bias conditions. Now what about forward bias? Well, if we have a positive bias, that means our voltage on the left side is larger than on the right, then we will have some current flow. So the way to notate that would be that if I is more than 0, then V will equal 0. So that is, if there's any positive current, then there'll be no voltage. And of course, the equivalent circuit for that is simply a short circuit. So there's no voltage change across there, but there is current flowing through it. So that's the most ideal diode model that we can use. Two very simple equivalent circuits. Now we move on to the constant voltage drop model, and we can immediately see from the IV curve here that it bears some similarities to the ideal model, but there's a slight difference in that we have this offset before we start conducting current, and we call that VF, the forward voltage. So in the reverse condition, exactly the same as with the perfectly ideal model, except now our condition will be that if V is less than VF, then we have I equal to 0. So we have this new threshold voltage here effectively, and if voltage across the diode is anything less than that, it's not going to conduct any current at all. It's basically an open circuit, as shown next to the diode circuit symbol here. in the reverse bias condition, we still have an open circuit. Now in the forward bias condition, we effectively have not just a short circuit, because then there would be no voltage at all, but we have a voltage source, VF. So you can simply replace the diode in the forward bias condition with a voltage source. Now this model is in many ways a lot more useful than the purely ideal model because it's much closer to reality. In our real diode IV characteristic, we can expect a curve that looks a little bit more like this line in the red here. So of course that is still quite different to the blue curve, our idealized voltage drop model, but you can see that it's quite close, and some of the key characteristic there is that there is this turn on voltage, which we've simplified here as a single voltage VF. But in reality, there's a relationship between the current and the voltage. So at any single point, that diode is effectively has a resistance, a dynamic resistance. But in our constant voltage drop model, we just assume that resistance to effectively be zero, and as soon as the threshold voltage is passed, the current will flow. Now a typical value for that forward voltage would be something like 0.7 volts if we're talking about a silicon diode. For other types of diodes, it might be smaller or larger, so for germanium, maybe around 0.3. For an LED, you can expect a higher voltage drop across that, so around maybe 1 volt. So that's giving you a bit of a summary of two of the most common and simplest ways to model a diode within your circuit, and how to replace it with an equivalent circuit as needed, where of course you need to know the biasing conditions. Is it in forward or reverse bias? So once you have that information, you can appropriately replace it with a short circuit or an open circuit or a voltage source, depending on the model that you're using.